Hello.
Good day.
Yeah, I'm here for this class. I'm just checking it out.
So for as folks come in, traditionally in these learning sessions of ours with This Week in ML, we seem to start a few minutes after the scheduled time, just to give a lot of folks coming in, folks trickle in. And so good morning, good evening, everyone. My name is Mash. I will be your teacher today, but really just someone who's going to help us walk through the material and content. What I'm sharing with you are just my private notes. I'm just going to pull it up just for a moment to walk you through our goals for today. What I'm hoping to get done with everybody over the next couple of hours or so. My estimation is we may, depending on how the discussions go, we may go a little bit over that. So please help me stay honest in trying to bound our session to the appropriate amount of time. But what I'd like to do as we start this journey for this entire class, I want to help us go through setting up the coding environment very quickly, make sure everyone knows exactly where to go and how they can set it up on their own respective machines. I can speak mainly to the Mac OS Linux environment. Those of you who are on Windows, I'm some of the things I may mention may not work quite as easily, but I ask others who are more familiar with Windows to be able to jump in and assist. And then we'll go over the different areas where the content for this class is located, where it's saved, so you all know where things are. I think there are different, a lot of the content is stored in different folders, links, Google Drive versus GitHub, and so on. I just want to make sure we all understand where what is. And then from there, we get into the core session. And for that, rather than watching the videos or doing any kind of silent reading, for my part, for my session today and next week when we do the practicum, I'd like to actually go over the content together. If we come to sections where it's useful for us to refer to the video, I've gone through them and I'll point you to, here's a link that takes you to the exact time slot of the videos. Take 5 minutes to watch it on your own rather than us sharing our screens and so on. Watch it on your own, and then we'll come back in 5 minutes and pick up the discussion from there. And to that, what I'm hoping to do is get us through Jan LeCun's lecture 1 and get us to a point where we're prepared next week to do more of the linear algebra and actually work through some of the notebooks and maybe even on a white screen work out some of the math involved so that everyone understands and has a strong foundation of going into next week as we build up, a typical PyTorch neural network, implementing that, and then going on to Mayank after that, who will help us understand more about convolutional neural networks. Does that sound like a good idea? Do you guys want to amend anything? Please do speak up. We've got a fair number of people here, so don't all speak up at once.
Sounds good, Mash.
Perfect. Well, we're 7 minutes in. Shall we get started? Let's do that.
Yep.
So the first thing, all of this material, let's go set it up. And so the first place to go is Alfredo Canzini, the teaching assistant for Jan LeCun's class. His GitHub repo @cold. @cold is a play on his first name Alfredo, Italian, which literally translates to Alfredo @cold. Funny guy. He's a friend of a friend. And so if you go to his GitHub repo for PyTorch Deep Learning, presumably it's his most popular repo, and follow the instructions on the README for that repo. He does provide step-by-step and how you can clone the repo and set up the Conda environment, this PDL Conda environment, to keep going. Now, for my part, I used Visual Studio Code. Just one moment, let the terminal pop up. And what I do not want are turn off my other it's fine. Sorry about that. If you just use your own terminal, clone the repo. Once you have your repo set up, you can kick it off. And that did not do it. I'll have to play around with this a little bit, but you get the idea. Any questions up to this point? And others, please do jump in. Those with a lot more experience with setting up environments and anything as we begin to do this, please do jump in. All right, once you have the environment set up, following the instructions over here, there's yet another website for the class. And so this one is on @cold.github.io. The other repos were on github.com. This one is this. You can also link to it from here where he mentions there's a companion website. So this is a companion website. This is the website that was used to prepare all of our sessions. And if you go to the top page, today we'll be covering the lecture session, History of Motivation and Evolution. The resources used for this class is just the YouTube video, and we'll get to the Google Drive materials in just a moment where the slides are posted and so on. Next week, we'll do the practicum, and so then on to stochastic gradient descent, backpropagation, and setting up a basic neural network in PyTorch, and then on to convolutional networks and thereon. And so for each of these sections, they're split up and organized by weeks. Again, we'll cover 1.1 and 1.2 today, 1.3 next week. And so let's move to one other location that is important. Bear with me. This material. So the notebooks are on the GitHub repo, but if you go to the Google Drive, which you can copy down, contains a few things. The slides, all of the slides that we will be covering. Today we'll be doing slide 1, the intro. This is what you see over here. It's 66 pages. We'll be going through that just as Jan LeCun does in his class, but going at a faster pace, focusing really on the meat of that lecture and so on. We also have here the homework sets. I haven't really, I think we all need to have a discussion on how we're going to do the homework problems. And of course, in the class itself, there is a competition at the end, sort of a capstone competition, if you will, involving autonomous driving. So as we get deeper into this journey and this course, we can all decide if it makes sense for us to try to do that competition as well. So in the Google Drive repository, the TA, Alfredo, has set up his page where he provides similar information. But within the class, they do have, for the participating students, they do have a requirement that everybody take notes, and they form themselves into groups of 3 or 4 folks and write roughly 300 words in notes and share that with one another. And if that's a way that helps you all learn, great, please do consider doing that, and so on. I don't know if we have that requirement, but at least we'll do our best. All right, let's go back to where we were. We covered the tips, and if that's everything, we can start to jump right into the course. Just by show of raise hands or something, did anybody not get a chance to watch the video? The video is about an hour and 45 minutes or so. Okay, see about 3 hands, folks, out of all of ours who did not see the video, and that's fine. We're all just trying to learn together. I just want to get a sense for how much of time we want to spend to the video. I do ask, as we go through this, for the majority of you who have watched the video, please participate in this discussion as we go through this. You don't want to spend the next 2 hours listening to my voice. I love the sound of my voice. I'm sure you won't. So let's have a spirited discussion, group discussion, and help each other learn. Let's just get right, since we're moving along pretty fast. Any questions before I go straight into the lectures on setting up the environment and the notebooks and so on?
Not a question, but I've seen that sometimes conda activate is the command to activate an environment. Sometimes source does not work. I don't know the exact difference, but you could try that out.
Right. Yep.
Yeah. Okay.
Conda activate. I don't know why I copied source. Should have noticed that. Sorry. But now that I have this, if I were to do Jupyter Notebook or Jupyter Lab, I'm just one of those guys, because I use multiple browsers. I put in with the key command no browser because, oops, if I could spell. There are a number of other. Oop. Wrong character erased. Wear glasses next time. All right. Let's just go into here. And it's probably going to point me to God knows which directory of mine. Yeah, probably the wrong directory. But you guys get the idea. Once you have it, it does work. Blah, blah, blah. And what's neat is Alfredo has made sure that the necessary packages associated with PyTorch are available. I think you may have to update NumPy from the version that's in the Conda, that's defined in the Conda environment. But that's it. Once you have that, you're all set, ready to go. Don't really have to fiddle around with too much to start using the notebooks. I do recommend, if you know how, clone these notebooks to your local machine. And from time to time, if you do see that they updated any of the repos, which looking at the date times for these notebooks, they haven't been touched in over a year. So I doubt that anyone's going to make any major changes to them. So you may not need to update your local repos, but still, you'll have them, and we'll refer to them quite a lot more, I'm sure, in future weeks. All right, so let's get to it. So Jan LeCun starts with laying out exactly, the course plan in his own interesting way. He litters it from time to time, if you've all noticed, with his own very specific views, what makes him different from other well-known luminaries in the deep learning field. And one of the things that he mentioned, and this came up from in our last class session last week, Jan LeCun's notion of self-supervised learning. And we all sort of wondered, well, what exactly does he mean by self-supervised learning? And so we are going to get deeper into that in this course, but it won't be a topic for today specifically. And so the inspiration for deep learning, he goes into, it's the brain. You guys have, I'm sure, if you're in this course, you should at least have seen or read about some of the history of how the understanding of neural networks coming from our studies of the brain biologically inspired our sense of building these mathematical algorithms for a neural network. It's a simplistic way to say it, because in the last 10 to 20 years, as Jan LeCun said, that view of using the brain as an inspiration stuck around for about 4 decades, until about the aught years, when we began to realize that view of thinking of it as the brain sort of was very binary, and that linear representation didn't really allow you to scale your learning models. And so the idea of using the nonlinear learning models helped to allow us to okay, here's how you do stochastic gradient descent. Here's how you can build neural networks that optimize a lot faster and a lot more efficiently, I think is the word. He goes into some of that, describing initially we had perceptrons. There was yet another one that was different from perceptron, Adaline, but that didn't seem to take off too well. But the general idea is you have a lot of features and weights that come to a function where you have a threshold If it's above a certain threshold, it gets one value. If it's below that threshold, it gets a different value. And so the standard paradigm for identifying any kind of a pattern involved two parts. One was figure out these features so you can have these data points. And then you have this classifier, which just is based on this threshold, what he calls here this threshold element, this thing. And that was your traditional approach for the longest time. And it was only after in the odd years when Jan LeCun himself, his particular paper, one of the things that I have considered is perhaps we might want to review next class, depending on how our conversations go today. We'll go through and review his paper next class to get us to a point where we can start to think through the algorithm design for neural networks. He did say, well, let's not do this hand engineering of features to extract out the most meaningful feature elements that are incorporated into the model. Let's incorporate all of that into this trainable part of the model. That's where it becomes deep. Any questions up to that point? Any reactions? Better way to explain what I just said. Shreyans, you've got your hand up. Do you have a question?
No, I don't think like it's on, like it's up from the previous thing, I think. I'm not sure.
Okay, all right. Don't worry about it.
Yeah,
Thank you.
I think it's off now. Yeah.
Okay. All right. So he goes into, hold on, let me pull up my notes. So this, we covered the standard model of pattern recognition consists of that feature extraction and trainable classifier. And there was one important point that he did make in those earlier ways of doing this. If you have layers that are just scalars, then the dot product of linear layers is always going to be still linear. And that's part of the reason why these models didn't work. And you needed layers that were nonlinear. And that's where he begins to explain a little bit to this. This is where things start to get deep. And this is where how shall I put it? You can have simple units, and all the different layers, and then you have your weights. But if the weighted sum is then passed through this nonlinear function being down here, something like this, then you have an overall function that is a lot more efficient. So that's the general idea. And what you're trying to do, your objective of using this function and this approach is, of course, designed around gradient descent. So you're trying to find the functions, this involves a certain amount of different calculus, differentiation. You're trying to find that global minimum. And we'll probably spend a little bit more time next class on that. But for now, let's keep it at his analogies, which is it's like walking in the mountains in a fog and following the direction of the steepest descent to reach a village in the valley. So one of the things I wanted to do here, of course, is let me pull up the slides. I want to have both of these side by side. So as we go through this, when you look through the materials, please do look at two things, the slides as well as the TA's notes. Okay. So we've covered perceptrons and adelines, pattern recognition and gradient descent, which is where we are here. If you, if anybody needs to know which part of the lecture that this was from, this is the link over here, which will point to second towards the bottom, 1461 second mark in the lecture. This is where Jan LeCun starts to go into this idea of building up to stochastic gradient descent. So the more efficient way to try to get to this global minimum is by stochastic gradient descent. So what we're trying to do is minimize the average loss over the training set. So the step is take, and we're on this slide 13. And so the step is we take one sample, or like a small group of samples, then calculate the error. Then for that, we have a gradient descent. And we do that, and then we take another new sample, get another new value for that error. And so we have a whole bunch of these gradients, descent values, and we take the average of that. Because each gradient will be in a slightly different direction, of course, because you have different samples, take the average of that, and that becomes what the direction that you go. The selection of which samples that you take from your data set, that those little samples to calculate each gradient, that is done stochastically. You pick randomly. And that works a lot more efficiently than there was a question that a student in the class had asked, well, isn't it computationally feasible to take the entire data set and calculate the straight gradient descent point? And Jan LeCun replied, yes, it is now computationally certainly feasible to do that, but it is not faster or more efficient than stochastic method. A lot of this is proven empirically, as opposed to someone doing the perfect research and saying, here's definitively why that's the case. So he mentions in the notes here, two of the main reasons for using stochastic gradient descent are that it helps the model to converge fast empirically if the training set is very large, and it also helps better generalization. What that means is you're going to get similar performance, the speed at which you reach that global minimum for your data on different types of data sets. Now, note, of course, that stochastic gradient descent, you're calculating negative gradients because you're trying to converge. And again, that calculation of negative gradient, that's also the idea of, I know you guys can't see me gesticulate with my fingers, convexity. That convexity, the notion of convexity comes from the fact of it's a negative gradient that you're trying to get. And if there's an interest, we'll dig deeper into this next class. So that stochastic empirically converges faster than the true gradient descent. And in Jan LeCun's own words, noise is good for you. So this slide here, slide 13, computing gradients by backpropagation. This is the part that builds on his paper, this paper. Scaling, and it's from 2007. So I understand it is dated. It is a fairly long paper, about 41 pages. But it does seem just, I did a quick read, didn't do a full careful read as I used to do before. It's a fairly good explanation of this way of building and understanding a neural network. So it is, I sort of left it open if we should begin next class session with that paper. Right. Computing gradients by backpropagation. Again, here's the link to the part in the lecture video, mark 36 mark in the lecture, where he walks through all of this. Okay. And then he goes into the historical examples and how we built up to this notion, where we applied some of the biological experiment of understanding how the visual cortex works and the brain and so on. And he points to how he jumps at this point, talk about, well, he developed one of the early versions of convolutional neural networks when he worked at Bell Labs, AT&T Bell Labs. That was the LENet 5, and there were a lot of these videos that he showed of how his model worked. Here he is, and for some reason this video has been trending on Twitter lately. Not exactly sure why this came up, but I'm sure many of you have seen this video. Andrew Ning in his classes uses this in terms of recognizing digits and numbers. And so he built on, well, you begin to use these convolutional neural networks, and when fully implemented, especially with images, it allows you to create, where's that picture? These segments within the image, call it a mask. So within an image, you have lots of these different elements. The algorithm classifies and identifies with a certain probability that this element, and it'll put a shaded mask, like this blue mask over this image, to say this one has a 96% probability of being a van. He mentions and shows someone who was you could see from the shadow, was on a bike, had a camera fitted to the person's helmet, riding the bike through Washington Square Park in Manhattan. And as he was taking that video image, the model was then trying to classify all sorts of elements in that live picture. And so in some parts, like it said, well, this one, there's a highest probability that that little segment that marked by a certain color mask is a desert. Well, it's not really a desert, but that's the probabilistic nature of these things. Any questions up to this point? Wow. The general idea from this is, as you're doing, is backpropagation. And that's what you want to get to, is this understanding of, you're trying to compute that gradient descent. What you're trying to get to is a sense for, well, this backpropagation equation for updating the weights. So that's because of that whole convexity nature and all that. And these are nonlinear functions that you're using for each layer. You are basically inputting vectors, not scalars. And so more generally, these are multidimensional inputs, vector inputs. And so this backpropagation allows you to compute the derivative of the difference of the output you want and the output you get, which is the value of the objective function with respect to any value inside the network. Backpropagation is essential as it applies to multiple layers. And that's what you need to have. And that's foundational to how a neural network is constructed. Now, he mentions the experiment from Fukushima, who did a whole bunch of these biological experiments using animals. And these guys, Hubel and Wiesel, who seem to have a preference for cats and doing experiments on the visual cortex and the brains of cats. But Fukushima took his biological experiments and constructed what that model would look like. So those were the early architectures of a neural network. This is the part where I'd love for somebody to jump in and expand on this a little further if they have a better understanding of how this architecture builds up the notion of convolutions. Let me just take a quick sec to look at the chat. If there are questions there.
Hey, Mash, can you hear me?
Yeah, I can hear you. Go ahead.
Okay, sure. So, sorry, don't know if you heard what I said. If you like, I can take you through the Hubel and Wiesel discussions and how that leads to CNNs.
Please, Dinesh, jump right in. Let me know which slide you'd like me to point to.
Oh, yeah, the name's Joseph.
Oh,
sorry.
Oh.
Yeah. So what ended up happening in I think it was like the late 50s, early 60s. Hubel and Wiesel, what they did is they tried to understand the cones in the cornea and basically tried to understand the neurons. What they did is they actually tied down a cat, obviously, so it wouldn't scratch them, and put a white or a board in front of the cat. And they put probes into just specific neurons and tried to identify if there's any electricity that actually went through them. So what they did is they flashed pictures in front of the cat, and the experiment was frankly a dismal failure. So what ended up happening is that as they were packing it up and they were moving the actual board, the neuron fired. So what they quickly realized was that that particular neuron fired on a vertical line. So light bulb went off above their heads and they started playing with other neurons, and they realized that other neurons would fire on horizontal or diagonal lines. So after experimentation, they figured out that there are other neurons that fired on more complex things like rounded edges, and others that would actually then fire on triangles, but not on straight lines, horizontal or vertical. So they quickly came up with the concept of that there's a hierarchical nature to the neurons. There's the base level neurons, which fire on basically straight lines, horizontal, vertical, diagonal, whatever. Then there's a second level that would fire on corners, circles. Third level that would fire on circles. Then the fourth level that would be, firing up on, for example, more complex patterns. So out of that, there was born the concept of CNNs, which is that you have a hierarchical structure and you have more complex shapes that the neurons figure out. And that goes back to, I think, what the Kuhn was saying earlier, that there's a hierarchical, I forget the word he used, but there's a hierarchical aspect to CNNs and
Is it
NLPs.
compositionality?
No, I'm trying to remember the word that he used. Compositionality he used. composition. Because if you look at, say, for example, a human face, it's made up of two eyes, and eyes are made up of pupils, and human face is a nose. So within a higher framework of a face, there's always sub elements. Within a bird, there's feathers. So that's why CNNs are much, once you train a CNN, it's applicable and you can use transfer learning to other systems. So anyway, that's just some background to what Hubel and Weisel were doing.
Very good, thank you. And so using that is what, as you just said, Joe, was the basis for designing a convolutional neural network. But I don't think they jumped to that just yet. That was still much early on. We're talking the 1960s, going into the 1980s. What was the bridge that got to Jan LeCun's notion of CNN?
I'm sorry, just to be clear, I mean, there was like a 40 years of wilderness before anybody got to CNN. CNNs are a concept that came in 2010, 11. So yeah, so it's not like these guys understood CNNs. It's just that they understood the hierarchical nature of neurons in the visual cortex.
Yep. Let's jump right to the next section, this evolution and uses of CNN. And so as speaking of what Joe just said, in animal brains, neurons react to the edges that are at a particular orientation. Groups of neurons react to the same orientation replicated all over the visual field. And this is where Fukushima is exactly as Joe just described. As a result, the shift of the picture will not change the activation of simple cells, but will not influence the integrated activation of complex cell convolutional pooling. It was in 1990, Jan LeCun, referring to his 1990 paper, used backpropagation, that idea, to train the convolutional neural network to recognize these handwritten digits. And there were several code files, and I wonder if one of them actually lays out and builds up this handwritten recognition. But honestly, this is the deep learning model that we all seem to have access to. This is, taking MNIST and building a prediction model, the prediction model neural network using the MNIST data set. All right.
I have a question. So yeah, it's to the group. So did they know that? Did they make CNNs in order to capture in order to capture information in a hierarchical way? Did they know it when they were inventing CNNs, or did they just observe that it just learns information in a hierarchical way? Like, was it designed that way, or it just happened naturally?
If I could jump in, the fundamental problem that you're up against is this, that the features that you're using you don't know how to process them. So what you've got with an image is that you've got, say it's 28 by 28, that's like 768 dimensions. How do you massage this in such a way so that you can then do classification? They didn't know. So where CNNs come out of it was, let the neural network figure out the features, the actual deeper level features. So that was the concept, that the compositionality, each of the components of the picture could be identified through each of the subsequent layers. And it was more a matter of like chance, and they were like playing with it, and as opposed to pure design.
Okay, got it. Thanks.
Well, one thing, if I could say, is this: when I was learning machine learning, one of the things that really helped me is understanding the concept of topology. What helps me tremendously is thinking about data has shape. What you're starting with is pieces of data, points of data in multidimensional space, essentially. And what you're doing is you're mapping that input to the output. A lot of the times you can do that very straightforward with linear models, with SVMs, etc. That's pretty straightforward. But if you're trying to do image recognition, that mapping is not easy. You've got to go through a lot of transformations, and that's where deep learning is. So if you think about it as curve fitting or mapping shapes, then it starts to make a lot more sense.
There is. I don't want to switch to another notebook. I did have a notebook that I think walks through the code for this, for exactly what Joe just said. But I need a minute or two to get that set up.
While you're doing that, let me put something in the chat. I'm a big fan of Gunnar Carlson, who talks about topology. There's a YouTube link I've just put up. It's in about an hour, but it's well worth going through because he explains topology and how it relates to machine learning. And that really helps if you're trying to think through things like GANs or other advanced concepts. If you have half an hour or an hour, just quickly go through it. It's well worth it. While you're doing that, let me just throw this out there. If you're talking about neural networks, fundamentally, you just need two layers to map any curve from one curve to another. I think that they talk about it on the actual video. So why do neural networks have, dozens, over 100 layers? And what those additional layers do is they go through and perform that hierarchical compositionality that's required to extract the deeper meaning in CNNs or NLPs. And then that's what they're doing. They're basically doing feature engineering and extracting information from the image or whatever, so that the last layer can do its job of doing classification or regression. So that's where that's coming in. So that's what mimics the brain and the actual visual cortex, because you've got all these additional layers who are extracting all this information. So if you look at a bird, the first layer just sees an outline, but the fourth, fifth layer sees the actual feathers and the context and things like that. So hopefully that helps.
Well, the other day I was, someone was trying to explain me the universal approximation theorem. So I guess, and he said that we were not sure if it was, if you have infinite power of computing, you could do the artificial intelligence with only one layer or two layers. So we were trying to know if it were one or two. So
what he's basically saying is that if all you're doing is curve fitting, i.e. you're mapping this point in and this point out, then essentially you just need effectively one layer to do the mapping and one layer which is just to do the classification, whatever. If you want to increase the level of accuracy, you can increase it to 2. That's just arbitrary accuracy. If that's all you're doing, 2 layers is all you need. All you need to do is maybe the number of neurons just get bigger and bigger, and you can fit any arbitrary curve. If you're trying to, but they won't work with images because you're not just mapping in and out. You need to decompose the image to identify sub information within the image. That's where the additional layers come in. So hopefully that makes sense. If you're just mapping, 2 layers is enough. If you're trying to extract additional information, that's where the deepness comes in.
Got it.
But theoretically, it should work for images as well, right? Why should it not work?
Because imagine if you've got a single image and you're trying to map it to a particular person, then sure. But what happens if the image is moved slightly to the right, or if it's upside down, or if it's a 15-degree angle? That doesn't help you. The image alone doesn't help. You need to deconstruct the image into hidden information, which is the curves, the angles, the mini shapes, the color of the hair, whatever. That cannot be done with 2. You need to decompose the image, and that's where the additional deepness comes in. If all you want to do is map A to B, 2 layers is all you need. And that's okay. I mean, if you're doing simple, linear regression, that would work.
Is that so that idea to me, when I say finance, I had my teacher for intrafinance was the guy who coined the words efficient market. Sort of jumping domains here, the idea that a market, trading, capital markets, stocks, all of that, bonds, everything is efficient. The idea is it's informationally efficient. And true market isn't just all basket of all available stocks in just, United States trading platforms. It is all of them. And then all different asset classes, literally all the way down to the shirt on your back. When you think of the whole market, and is that the same kind of idea, that compositional hierarchy? What you're trying to do is learn the structure of the world compositionally, all the different elements that make up what that is. So that little thing at the very end of the lecture with someone's, a woman's face, how many dimensions are there? And so he said, well, there's 50 or 60 muscles. Each of those are a dimension, and then each of the pixels and so on. So basically it's just really hard to understand all those informational dimensions that you have to disentangle and get out. Is that the idea of those different features? I might have lost folks on that analogy that sort of playing out in my head. Sorry about that.
So I think for an introductory class, it's kind of like, we can spend an hour on this. I mean, we can get into it, but the concept really runs into, imagine you have a spreadsheet and your columns are your features. That's the inputs, right? Every single column, every feature is a dimension. So if you look at a, the hand recognition, I think it's 28 by 28. Mm-hmm. If you take all of these and you multiply them and think about where there's a data in every single pixel, that is really 28 by 28, which is roughly, 768 dimensions. So each picture is a single data point within a 768 dimensional space. And I don't want to confuse people, but it's very difficult to do anything with that information. So what you need to do is decompose it so that you identify the curls, the straight lines, if there's loops. That's where additional layers come in, because they break it up into lower dimensions, and that's much easier to use.
So does the neural network architecture capture that, but we are not putting that as, if you have columns of data, even if you were to take an image, the 28 by 28, and each of those pixels, and you've got, you know, all this columns and so on, we're not creating additional columns of those informational elements. The neural network is.
It's defined by you. Essentially what you're doing is, if you think about this 28 by 28 image, right?
Mhm.
That ends up being inputs of roughly 768 dimensions, right?
Mhm.
So what the second layer is, you define. How many neurons in that layer defines the dimensions. And you put as many as you want, but the last has to be 10 because you want to output 0 to 9. So you define which dimensions, you define what it learns, and you just run stuff through it, and it'll identify attributes within those dimensions that you define. So if I define a second layer and it's got like 100 neurons, that's 100 dimensions. So I've gone from 768 to 100 and then down to 10.
Mhm. So that, okay. That's
So
just focusing, right? That's just focusing.
Yeah, I think the analogy Mash you were saying, right? For example, like the additional features in like an addition to the 768 pixels which we have right now, right? The additional features which that those are the features which neural network is creating on its own. So because like in a classical machine learning case, for example, if we are trying to fit a linear regression, right? So the feature engineering is done by the like the guy who is sort of creating the model, right? So in that case, like in this case, we are just sort of inputting the raw pixels or the raw data which we have, and the advanced feature creation is being done by the neural network itself. So it's like as we go deep in the layers, the complexity of the features increases, right? That's what like what Joe is saying. As we sort of go in the depth of the layers of the neural network, the complexity of the features increase. For example, the women's face example which you gave
Mhm.
earlier.
Mhm.
So if we take that example, for example, in the first layer, like maybe the curves of the eyes, nose, like maybe the upward curve and the lower curvature of the eye will be sort of getting captured. But I think as we go ahead in the deeper layers, for example, like the retina of the eye or the eyelashes or the structure of the lips or the structure of the nostrils or the nose, those are the advanced features which are getting generated with the help of the previous simpler features which we have created.
Mhm.
Using that, we are creating more complex features so that finally we can sort of try to classify or try to whatever the final problem is. If it's classification, we can classify an image
Yeah, more
properly.
efficiently.
Yeah.
Mhm.
There's a great little site which I'm going to dig out, but it basically shows how what data actually looks like in multiple dimensions, and it makes it a little bit easier. So I'll dig it out and send it over. But that kind of like explains, I think, what we're both trying to say.
Yeah, I think that would be helpful. For me, my struggle is I hear you guys and I get it in theory in my head. I'd love to be able to see. So what does that mean with the data? How is the data being transformed step by step by step?
I'll dig it out and give me a minute, but please continue. Sorry.
Okay. So a lot of these things now in the class lecture, Jan LeCun skipped certain slides that he has here on convolutional neural networks, how he builds it with partial differential equations, and how he solves for them and so on. And I thought that would have been a lot more useful. And this is the part where I thought, okay, I'm going to go through the research paper and maybe help us go through that in the next class. Didn't want to scare everyone off today, and I think it requires a little bit more preparation on my part too to be able to speak to it intelligently. That's what he does to finally get to some of these frameworks here towards the end. like, here's how the convolutional neural network architecture is laid out. And look, it still does something similar to what our original inspiration of that biological visual cortex representation.
So Mash, I sorry to interrupt you. Maybe you could do this at the end, but I sent you the link to projected at tensorflow.org. If you could pull that up.
Yes, sir.
This just helped me understand it a little bit easier. That's kind of why I did that. Okay, so if you choose the MNIST data, so this is going to take a few seconds. What this is this is trying to project multiple dimensions onto a flat surface. You know, humans struggle with anything more than 3 dimensions, right? So this is trying to convert it. So if you see where it's got like data, go to MNIST. Actually, if you go here, yeah, and go into Iris. Iris is a good example. Okay. Okay. And then see where it's got color by no map, select labels. Sorry, just down, there it is. Up to the right. Class. Okay. Okay. And if you kind of like scroll down, it'll zoom out a little bit. Oh, I'm sorry. No. It's actually with your. If you click on the thing, it'll zoom out. Yep. And then the other way. Okay, you're zooming in. Okay. Okay. So what this is, there's 3 classes: blue, red, and pink. And this is just the iris class. And if you move your mouse, you can see, you can actually turn around and see it. But okay, so this is where you could use 2 layers or just a simple linear classifier, SVM, something like that. Easy to separate the classes, absolutely easy, because you just draw a straight line through them. You could have a 2 layer neural network. It'll separate these 2. Easy. You don't need more than 2 layers. But then if you change the data to something like MNIST, this is the 10-digit data that's the one. Okay.
By the way, Joseph, you have rights to move my mouse.
Oh, I'm sorry. Thank you. Thanks. I didn't mean to take over, but this is kind of like, you know, I love the topology view of machine learning. It helps me understand it so much. So sorry for jumping in.
No, this is great. Please continue.
So what we're looking at is the data, but in oops, stop it. Okay, sorry, I'm trying to stop it. Okay, I'm just going to go and click on label. Okay, so what we're looking at is the data that's in 768 to 784 dimensions, I should say, because that's 28 by 28. Okay, now I'm just going to zoom out a little bit. Now, what you see is the different colors is that's the 10 different classes, whether it's, you know, the number 0, 1, 2 up until 9. Okay, you can see this number here, which is the ones. The ones are easy to classify because they're all kind of by themselves, and you can draw a straight line. There's a bit of an overlap to 7s. But if you look at the 3s, how do you separate them from the others? It's next to impossible because your error rate is going to be very high. So this is where you need multiple layers, because the data as it just stands the way it is next to impossible to separate. If you had just a, you know, no matter what you do, linear classifier or just if you use whatever, 2-layer neural network. But what you need to do here is then run multiple layers of a neural network to identify the curves, the open loops, the closed loops. That then makes these classes separatable. That's where the additional layers come in, if that makes sense. And you can see that they're so entangled that it's next to impossible to separate them. But if you then identify richer, more hierarchical features, it's easier to separate them. And this is how, like, it helps me understand what we're actually doing underneath.
Very cool. This is really cool. Thank you, Joseph.
Sure. And thank you for volunteering to be first off the bat. I know it's always hard. Thank you.
Shreyans shared one more link, playground.tensorflow. Let me open that up as well. Shreyans, do you want to walk us through this? So what this does is there are different data sets, of course, and this is the typical neural network model as it tries to converge and what that begins to look like. And you can change how many features you want, if it's just 2 features, and how many different layers that you want to have, and how many neurons per layer, and so on and so forth. And when you hit play, you can begin to see how it tries to create those classifications, the separations.
Yes. So, for example, if you start adding multiple layers, like if you start increasing the depth of the neural network, you will start seeing, for example, in the first layer, it's sort of just maybe detecting straight lines or diagonal lines, and then in the additional layers, as we go in the depth of the neural network, it starts sort of mapping, getting sort of you can say complex features and all, like a circle or some kind of a pattern, the data which is showing. So if you add maybe 4 hidden layers, or for example, and start play, you will see complex features in third and fourth layer. So I think this helps in understanding like the hierarchical nature of that, like what we were discussing earlier.
Mm-hmm. Indeed. So what we're dealing with here is all of those different dimensions. We just sort of jumped into, well, if you can begin to add a lot of dimensions to the data, right? Is that me? There is the, go ahead. All right, that's fine. The idea that natural data itself lives in sort of a low dimensional manifold, that manifold hypothesis that Jan LeCun tries to build. The general sense there is, you've got a set of all images, which can essentially be infinite, but then he says, well, the natural images are only just a tiny subset. Like pictures of people are only just a small set of all possible theoretical infinite set of images. And so when you're doing image recognition, is it just that you are trying to isolate, these models are trying to isolate to optimize a certain number of features that represent a person or that particular class that you're trying to identify, and so on? Is that the right way to think about it?
Yes, I would say the way I think about it is that what you're really doing is you're mapping the input space, the features, to the output space. The input space, for example, an image could have 768 dimensions if it's, for example, an image. But the output is a 10-dimensional manifold, which is 10 dimensions, which is the numbers 0 to 9. So you're always mapping a high dimensional space to a low dimensional manifold. And that manifold just means it's a surface, okay? So think about, if I ask you the question, where in the universe are you? The inputs to that would be, well, XYZ, it's time, the rotation of the earth, the seasons. It's like God knows how many dimensions. But the answer is simple. It's longitude and latitude. That's where you are. Right. So you're mapping high number of features, but to a simple answer, which is there. That's what the manifold means. Just you're mapping a surface, which may be flat or not, but that's the answer space.
Got it. But then how does the manifold jump to then the idea of representation? Isn't that like you're now, even within that flat surface of all possible images, you have to be able to find the factors of variation, what represents, okay, this is a van, this is a face.
Yeah, it's not a flat surface. It's just a surface.
It's just a surface. Yeah.
But you're actually right. You're actually traversing that surface. If you go from one to the other, you go from van to car to cat to dog. And so when you see those things like, for example, on the internet where, you transform a man to a woman with glasses, all you're doing is you're moving along that manifold. It's, in dimension with glasses, dimension of gender, dimension of height. That's what you're doing.
Oh. Got it. That's a pretty neat idea. All right, folks, we've moved very fast through this, much faster than I'd expected. I think I've gone through what I had set for myself to be able, thinking that we would cover what would take about 2 hours or so, but we went through it faster than I expected. Let me go back to where we were. Bear with me. So move this back exactly the way I had it. Right. So he talks about that, the feature extraction and then learning representations, which we just discussed, and sort of ended the lecture pretty much what felt like at a fairly climactic moment of going into, well, what more is there? So that's where we are. That's where we are. On the chat, there were some comments about the support vector machine, which does take multiple dimensional problems and reduces it to a fewer set of dimensions, 2 or 3. Jan LeCun made the point that no, that doesn't really, that's not as useful. And then he also mentioned, well, there are also other people who try to extend that idea into extreme learning. And he didn't seem to like that at all. That was his view. So I think that's the last of what we will mention. We'll go with Jan LeCun's view of the world. That's it. That's all I've got. My goal, again, for continuing with this is next week, hopefully we'll be getting a lot more deeper, expanding upon this slide 56. Sort of the math involved. This part, and this comes from that 2007 paper, and he uses circuit gates, including negative and, where he says, it can be used to find any structure of a function. Is that something that would you guys think be useful, starting with this specific paper and actually working through this paper quickly, not taking the entire 2 hours for it, but maybe for about 30, 45 minutes to go through this paper, and then going through all of the notebooks, the code that the TA uses in order to get a strong sense of this is what we're talking about with the math behind and the linear algebra behind neural networks. Can I get just a few people chiming in, say, yeah, that makes sense, or no, modify it?
Yeah, sounds good. Sounds good.
Okay. All right. That's all I got.
Okay,
Thanks, Mahesh. This is great.
it
Of
was
course.
good.
Gautam, do you want,
And
Gautam, Joseph, do you guys want to, anything else you want to add?
no, I think the only thing to be done before the next class is to go through the notebook and run through the code. Yeah.
Which notebooks we should run for? Well, I didn't come the first
Okay.
session, and I
So
just joined it.
okay.
Sure.
So in the website, okay, yeah, Mash, you can go ahead for sure. Yeah.
All right. So let me repeat some of the things I shared earlier. There are two different websites that you start with. One is, of course, the github.com at Cold and his PyTorch deep learning. So set up your, follow the initial README on this, set up your environment. Right here, he has all the main notebooks. So some of what we will cover next session will be 00, logic neuron and tensor tutorial, and space stretching. These three are referred in the notes from the lecture that we just covered, as well as this. Now, the other one is if you go to the github.io, this is the course page, and here are all the notes. Take a look at what we discussed today, number 1.1 and 1.2, and read ahead a little for 1.3. And this is what we will effectively cover next week. And the whole purpose of going through the paper is hoping we'll use the parts from this paper, the understanding the learnings that help us get through this material around neural network, what's going on, and so on. And I'll do play with those two websites, the TensorFlow websites that Joe and Shreyans shared, this projector.tensorflow.org and playground.tensorflow.org, to get a sense for what's going on with the data and so on. And we can probably we will surely refer to it next class as well. Does that help?
If you just joined, or if you want to see how to make sure that you keep up with the class, I've posted a message earlier this week in the Slack, and I just posted a link for you in the chat. I pinned it to the channel, and it basically collects all the resources for the class and tells you where to find everything. So there's the main course website, there's the GitHub repo, there's it shows you where to find the one-page summaries of the lectures, the videos, and so on. So and the slides. So if you're going to take the class, you should get yourself organized and be aware of where all the resources are, so that you won't fall behind and realize after 3 weeks that, hey, I should have read this piece, or I should have looked at this thing, or whatever. Anyway, they're all organized for you in that post that I made. So have a look at that, and that could be your guide to exploring the course resources.
Here, Joseph is referring to this main course website, GitHub repo, set up your environment, and so on. And there was one more question about whether we'll use Google Colab. I think for now, we're probably okay using our own machines. But by all means, if you prefer to use Colab or have a pro subscription to Colab Pro, you can still do the same thing. A lot of different ways to run Python. That's it. Gautam, Joseph, back to you guys.
Thanks a lot, Mash. I really appreciate your taking the lead.
Yep. Thanks everyone for joining.
Any questions that people have about the course or about what's happening during the course? I think somebody asked about what topics we're covering and so on, but you can find that out by looking at the course syllabus. We're just going to go through the course straight. We're not going to focus on these topics or that topics. We're going to do all the lectures. Any questions?
So I have a question about this degrees of freedom idea, and I just wanted to clarify if I'm getting it as you guys are. So basically, when he is talking about this picture, portrait of a woman, and that it has much less degrees of freedom than pixels, it's like the same as say we have a series x, x squared, x cubed, and so on. And we can have this series, say 10 powers of x, and it is 10 features. But if we find this pattern there, we can reduce it to only a single feature, and it will still fully describe the data. And so what he was when he was talking about this representation learning and how you represent a portrait of a human. So the idea was that there is really much less ways to, we need much less variables than pixels on the photo to represent this picture, right?
Yeah. I mean, if you think about it, 1,000 by 1,000 pixels is a huge number of degrees of freedom, but these pixels happen to be organized in images, and the fact that the image represents something with a, it vastly constrains the degrees of freedom, right? I mean, because pixels in a face, or for example, if you know that the image contains a face, right? Well, faces have a certain shape, and they have eyes, and they have a nose, they have certain features, and every image is going to have those same features. So you're vastly constraining the degrees of freedom in that 1,000 by 1,000 pixels. So it makes sense. It makes sense that the thing should be representable in a lot fewer dimensions than 1,000 times 1,000.
And so if we move from here to this universal approximation theorem and comparing two-layer neural net, two-layer neural net making it wide enough, it may learn anything. So that's what might approximate any kind of function to arbitrary.
If you make it wide enough, right? So
yeah. But when you move from this, when you try to train this two-layer neural net, you don't take any use of the fact that of this reduced number of degrees of freedom in the picture. If you want to learn to map, say, a photo to person identity, and you use a two-layer neural net for that, you don't use the fact that you don't use any information, extra information. But if you use a convolutional neural net, deep convolutional neural net, you have you introduce two kinds of inductive bias. The first is introduced by convolution, which is locality. So we assume that there is a local structure to this picture. And the second one is compositionality, which is introduced by going to deep neural net from two-layer neural network. So that's how I
yeah, because people saw, when people first solved the MNIST problem, if you remember, usually they introduce a fully connected neural network with just one layer to solve that problem, right? And you deal with a 784 dimensional space, because the 28 by 28 pixels is a 784 dimensional vector. So as you said, if you do it that way, you're not making use of any of the spatial information at all. And so you could get a reasonable result, but you'll do much better if you use a convolutional neural network and make use of that inductive bias towards locality that you mentioned. Yeah, so that's a very good point.
Guess we'll cover a lot more of that next week. Okay.
Oh, and we should mention that there are still some slots in the in the schedule. So anybody that wants to can sign up to present something. Let me just give you the link again.
I think we've got a lot of them covered.
Oh, good. It's been happening since the class. Good.
It's just the later months in summer.
Right. And let's see. And there's one thing I noticed in that some people are signing up for just one slot, but if you sign up, it would be best if you signed up for both the lecture part and the practicum part, so that you're doing the whole thing. So if you want to reconsider that, you might do that. I think there's a fellow who signed up for I think it's Saad who signed up for energy-based models and self-supervised learning, and then he didn't sign up for the practicum, so I stepped in. But if Saad, if you want to sign up for the practicum, you can erase me and put yourself in there. And I noticed you also signed up for something else further down, where you just signed up for one part and you didn't sign up for the practicum. So I encourage you to sign up for the practicum too, so that so that it's sort of a continuous presentation.
The one other thing I'll share, I wonder if everyone's experienced, those who have coded with both TensorFlow, worked with Fast AI as well, which is sort of the API layer built on top of PyTorch from Jeremy Howard. Jeremy's Fast AI does seem to make using the PyTorch kernel, if you will, I'm not using the word correctly, but using PyTorch a lot more easier and more accessible to programmers. And TensorFlow is the same way. It leverages Keras as the API layer, making TensorFlow a lot easier and more accessible to developers. But if you're going to work with PyTorch, especially in this class, if you'll notice, a lot of the notebooks do require you to understand Python better. Did everybody get that same sense?
Yeah, but if you go in Jeremy Howard's Fast AI, it's the same thing. He makes tremendous use of complicated concepts in PyTorch, as certain of us knows, because he's been leading a class through the libraries, and so there's no avoiding it. You have to learn some of the more advanced features of Python in order to be able to build these things. Yep. Even Fast AI, Fast AI at the very low levels, yeah, you can put together a model in 4 lines to do, some simple image classifier. But at the more advanced levels, it's not easy. It's not any easier than just programming in Python and doing it yourself.
And getting the data ready.
Yeah, because Fast AI has such an intricate structure. There's so much. He's built, of course, a very nice, complicated library, but it's not easy to work with. There's a really steep learning curve. So I don't know what to say about that. You might as well just learn how to do it in Python yourself.
My motivation, I'll share my own experience. I've been doing data science and all of this for a very, very long time. It's more traditional data science, not applying deep learning in production models. And so I come from the biotech world, financial services and manufacturing and so on. And what I'd like to do is prepare data from those domains and develop them and build them and create these neural network architectures for those specific domains, as opposed to images and so on. And for the purpose of this course, I was hoping I could wow you guys and say, hey, let's skip the images data and the MNIST stuff. Let's use I try to use like a simple time series, stock price, and others, but trying to get the data set ready to use it with PyTorch, I couldn't get it done. And I spent out almost a day on it.
Wow.
Couldn't get it done.
Well, I think we're going to get into time series and stuff later on in the course. But as you point out, it's the whole thing is getting the data ready. That's where all the manipulations come in, and that's where all the complexities of Jeremy's FastAI library. If you really spend the time to learn it and so on, it can be a great tool for you. But it is a steep learning curve.
Yeah.
Yeah.
And Anand, to your question to me, kernel methods versus neural networks, no clue yet. I don't know. All right.
That's cool. Thanks.
Thank you all for giving me 90 minutes of your attention and time. Truly appreciate it.
Thank you. Let's see everybody next week.
Yep. Stay safe and stay well, everyone.
You too.
Thank you.
Thank you, Mish.
Thanks, Mesh. Thanks, everyone.
Thanks, Mash.
Of course, Joseph. Bye.
Thanks, guys.